You've probably seen a metal rod glow red, then orange, then white as it gets hotter. Seems simple, right? But around the year 1900, the smartest physicists on Earth couldn't explain something as basic as the color of a hot object. Not only that, their equations predicted something absurd: infinite energy, which is physics' way of saying, this is completely wrong. And that tiny failure, that embarrassment, is what gave birth to quantum physics. And today, that same idea is being used to build something almost science fiction: batteries that may charge faster by using entanglement. But to understand that, we have to start with something very ordinary: an oven. Imagine you turn on your oven and let it heat up. At first, it's dark. Then, as it gets hotter, it starts to glow a dull red. Increase the temperature, it becomes orange. Hotter, yellowish. Eventually, almost white. So here's a simple question. Why does the color change? What decides whether something glows red or blue? At first glance, you might think, well, hotter means more energy, so maybe it just glows brighter. But that's not quite right, because the color itself is changing. Not just brighter red, but shifting toward higher energy light. So physicists asked, if we take a perfect oven, something that absorbs and emits all light perfectly, what we call a blackbody, can we calculate exactly how much light it emits at each color? In other words, can we predict the color of a hot object? Sounds like a reasonable challenge. So they did what physicists always do. They wrote down the equations. And at first, everything seemed fine. For low-frequency light, like red, the math worked beautifully. But then they extended the same equations toward higher frequencies, toward blue, and beyond. And suddenly, the prediction broke down. The equations said that as the frequency increases, the energy doesn't level off. It keeps rising, and rising, and rising, until it diverges toward infinity. Infinite energy coming out of a simple hot object. That's not just slightly wrong. That's completely impossible. This disaster became known as the ultraviolet catastrophe. But here's the strange part. Real objects don't behave like that. A hot oven does not blast out unlimited ultraviolet light. Reality was fine. It was the theory that was broken. So now, physicists were in a crisis. Their best understanding of physics failed to explain something as everyday as heat. And then came Max Planck. Planck wasn't trying to revolutionize physics. He was trying to fix an equation, just make it match reality. So he did something bold. He made an assumption that had no physical explanation at the time. He said, what if energy isn't exchanged continuously? What if it comes in tiny, discrete packets, like coins, instead of a flowing stream? You can't have 2.3 coins, you can only have 2 or 3. Planck imagined that the energy exchanged between matter and radiation works this way. Not smooth, chunked, quantized. He called these packets Quanta. And when he used this idea in the equations, something remarkable happened. The infinities disappeared. The curve matched reality perfectly. Red, orange, white, exactly as observed. It worked. But here's the twist. Planck himself didn't fully believe it was a fundamental feature of nature. At first, he treated it as a mathematical trick, but nature doesn't care what we believe. Because soon after, Einstein took this idea seriously. He said, no, light itself behaves as if it comes in these packets. We now call them photons. And suddenly, this desperate guess became the foundation of an entirely new way of understanding reality: quantum physics. Now pause for a moment. Think about what just happened. To fix the color of a hot object, We had to abandon the idea that energy is continuous, at least in how it is exchanged. That's a huge shift. It's like discovering that what looked like a smooth ramp is actually made of tiny steps. Once you accept that, everything changes. Because now, energy isn't just something that flows. It's something that comes in units. And once you have units, you can store them, control them, manipulate them. And that brings us to today. Imagine a battery. A normal battery stores energy chemically. You charge it, electrons move, reactions happen, energy is stored. Simple enough. But now imagine a different kind of battery. Instead of storing energy in chemical bonds, it stores energy in quantum states of a physical system. A quantum battery. At first, this might not sound very different. Energy is energy, right? But here's where it gets strange. In the quantum world, systems can become entangled. That means their states are no longer independent. They behave as a single, coordinated whole. Now think about charging a battery. Normally, if you have many units, you charge them individually or in parallel. More units, roughly more total time or resources. But in a quantum battery, if the units are entangled, they don't behave independently. They can respond collectively to the charging process, almost like a choir singing in perfect synchrony instead of individuals warming up separately. And when that happens, something surprising occurs. The charging power, the rate at which energy is absorbed, can scale differently than in classical systems. In some models, it increases faster than you'd expect from independent units. This is often called a quantum advantage. And recently, researchers demonstrated a key step toward this idea. A system showing superabsorption. Instead of each unit absorbing energy on its own, the system absorbs energy collectively, like a group of antennas acting together. The result? Potentially faster and more efficient energy uptake under the right conditions, all because of the same fundamental idea, that energy is quantized, and quantum systems can act collectively. Now step back again. The problem started with a simple question. Why does a hot object change color? That question exposed a deep flaw in classical physics, forced us to introduce quantization, gave birth to quantum theory. And today, that same idea is being explored in technologies that may reshape how we store and use energy, from glowing metal to quantum batteries. But here's the deeper insight. The universe didn't have to be this way. Energy could have been continuous, smooth, predictable, but it isn't, at least not in how it behaves at small scales. At its core, reality is quantized, built from discrete interactions, and those quanta don't just sit quietly. They interfere, they entangle, they cooperate in ways that challenge our intuition. So the next time you see something glow red in the dark, a stove, a filament, even a sunset, remember this: you're not just looking at heat, you're seeing evidence of quantization, the idea that reshaped physics, and may one day power entirely new technologies.